we will just review how to find derivatives today. And we will see some examples, and we will start deriving rules for the derivative. Okay, so once we have those rules, we will be able to find the derivative of a given function, of any function. Okay, so let's get started with an example which we did similar problems last week. So we want to find the derivative of the function f of x equals x cubed plus 3. So let me remind you the formulas we were using. So normally, if you want to find the derivative of a function at a point, at a specific point, you can use two formulas. You can just find the limits of the slopes of the secant lines. So how do we find the slope of a secant line? So we want to find the derivative of the function f of x equals x cubed plus 3. So let me remind you the formulas we were using. So normally, if you want to find the derivative of a function at a point, at a specific point, you can use two formulas. You can just find the limits of the slopes of the secant lines. So how do we find the slope of a secant line? We just take a point which is close to that point A, just pick an x value close to A, and evaluate the slope of those two of the line that passes through those points, x and a, f of x and f of a. Okay, so we just find the slope, and as x approaches to that point A, this gives us the derivative. So this expression, remember we said that this expression is called the derivative of the function at A. It is the slope of the tangent line. So if this is the point A and this is the graph of f of x, the slope of this tangent line is this expression, is given by this expression. Okay, so this is the slope of the tangent line. This is called the derivative. This is also called the instantaneous rate of change in f, okay, in this function at that point A. Okay, so this is how we defined the derivative for at a point. And we also used another expression which gives us the same result. So we said that we can just measure the distance between x and a, and we call it h. So we can say, just pick the point, sorry, it's supposed to be a, so just pick a little distance h and evaluate the function at a and at the point a plus h. Okay, so the distance between the points you pick are h, and so the distance is h between the 2 points, a plus h minus a, and we take the limit as h goes to 0. Okay, so as the distance between the 2 points get close to 0, then this also gives us the same value. So these are both equal to each other. Okay, so the same thing stated in a slightly different way. And so these are derivatives at a single point. Then we said that we can just extend this idea to obtain a formula throughout an interval, let's say, okay, where this is defined. Instead of finding this value, so these two expressions will give you some numbers. Okay, instead of obtaining these numbers individually at each point, we can just come up with a formula for the derivative. Okay, so at any point, instead of a specific point A, we can just find the derivative function. Okay, so let's call this the derivative function. So this is now going to be an expression. It's going to be a function. And when you plug in a value of x, you will find the specific slope of the tangent line at that point, okay, for that specific line. And to derive this function, we just make use of this formula. So the limits as the distance between the 2 points get close to 0 of the function evaluated at x plus h minus the function evaluated at x divided by h. So realize the similarity and differences between the two formulas, these two. So the only thing that's different is the first one is at a and the second one is at x. So in the first one we have a plus h. So we would like to find the derivative of this function. I just highlighted in aqua color, x squared plus 3. Okay, so we will just apply the formula which I just erased, and we can just note that down again. So the limit, okay, what was that formula? The derivative function. Okay, so we will find a general formula for the function, not at a single value. Okay, the question just asks us to find the formula. So we will talk about the power rule today. So you won't be able to, you won't need to go through these steps. But let me first remind you, like just rewrite the formula again. So this is what I just erased. This is the formula to find the derivative of a function. Now, our function is x squared plus 3. So we will evaluate this function at x plus h. Okay, so just copy the limit part, limit h as h goes to 0. And how do we evaluate this function, f function, at x plus h? So we should plug in x plus h. Okay, so when you plug it into the f function, we are finding f of x plus h. What should we do? We should square it and add 3. This is the f function, right? Agreed? So we just plug in into this function. We just plug in x plus h. So f function, okay, f function just squares everything and adds 2. So we just evaluate it at x plus h. This is what we get. So this part is f of x plus h, right? Minus, now we will write f of x. So we will subtract from this expression f of x. And what is f of x? It is simply x squared plus 3. So just write the two expressions and we will expand them and simplify and see what we get. So limit as the distance between the 2 points x and x plus h, it go to 0. What do we find when we square x plus h? Okay, so I just put that for you. So when you square a binomial, we just multiply x plus h by itself, and when you FOIL out, you will have 4 terms, and the middle two combined, you will have this middle term, plus 2xh. Okay, so, and we have plus 3 in the first parenthesis, minus, so let's get rid of the minus, let's distribute that minus. So what should we, oops, sorry, I meant to delete these. So we should subtract x squared and 3. Okay, so when we distribute this minus, and we have h in the denominator. So what cancels out? X squared minus x squared, 3 minus 3. So what are we left with? The limit as h goes to 0, 2 x times h plus h squared over h. And can we factor out a common h? So remember, we should factor out to be able to simplify things. So when you factor out to h, we will find 2x plus h divided by h. Okay, so one of the factors will go. We will find 2x plus h. And what does this result with? H's will cancel. And can you evaluate this limit? What is the limit as h goes to 0 of 2x plus h? What should we find here? So remember, as long as the function is continuous, it is defined at that point, we can just plug in the value. We can just evaluate this expression at h equals 0, right? So we can simply plug in h equals 0. What happens then? We find 2x plus 0, which is simply 2x. So what did we find here? We found the derivative of the function f. So let me copy them here, maybe different color. So the function f is x squared plus 3, and it is derivative. We found the derivative, the formula for the derivative to be 2x. Okay. So let's graph these, and we found the derivative to be 2x. Okay. So let's look at these two, and we will just see how they are related. Okay, so the red function is the parabola. You see the graph is a parabola, and it is equation, the formula for this function is x squared plus 3. Okay, so what do we see? Is this function increasing or decreasing for negative x values? So when x is less than 0, so to the left of the y-axis, is this part, is it decreasing or increasing? So the left part of this red parabola, it is in fact decreasing. So let me just show you here. So here, as you move from left to right, just look at the y values: 9, 8, 7, 6, 5, 4 point something, 3 point something, and 3. So the y values decrease. And what do we see for the derivative? So the blue curve, so the blue curve, realize here, it is less than 0. So the main thing you should pay attention is that the derivative here is less than 0. It has negative values, right? You see the values are negative. They are negative because negative slope means a decrease in the function, right? Decrease in the y values. And realize that here, as you have, as you move more to the left, when you see here, the decrease is steeper, right? So the decrease is steeper. So in fact, the derivative has a large absolute value, right? -9, -10. So the derivative has a large negative value. But as you get close to 3, as you get close to this point, the function, the tangent, is still decreasing. The function is still decreasing, but the slope is not that big. So here we have the derivative. Look at the y value as -0.9. So the derivative has, compared to here, which was like -9. So the function is still decreasing, but it is slower rate. Okay, so not very steep, but slower. And what do we see at 0? Okay, let me draw this line at y equals 3. So here, at this point, in fact, here at x equals 0, so we see that the derivative is 0, right? The derivative, look at the blue curve, look at the blue line. This is the graph of the derivative function. And when x equals 0, the derivative is 0. What does zero derivative mean? Zero derivative means that the function is not changing, right? There is the instantaneous rate of change is 0. So if you draw the green line, that is the tangent to our function, the red curve at the 0 point. Okay, so here the rate of change is 0. But if you just keep going to the right, so if you pick any point to the right of 0, so here the derivative was 0, here we see that the function now increases. And we can see from the derivative that it is greater than 0. So whenever the function is increasing, you will have a positive derivative. Here the derivative is positive. And again, so around 0, it is increasing but slowly. So we have like a less steep curve compared to larger values. So here, let's look at the change. The function is moving very steeply. Here, if you consider the tangent, it has a less slope, but as you move, it has a higher, like steeper slope. That is consistent with how we see the derivative function, the graph of the derivative function, which is the blue line. So the blue line has a larger value. So here, for example, the derivative is 10, and here the derivative is 1. So here, from here to here, the function, the slope is increasing. Okay, so we will see other examples and to compare a function and its derivative, how they look like. We just found an expression for the derivative of this function. So we found the derivative is 2x. Then we sketched the function and its derivative here. And so we saw how the graph and its derivative are related. Now let's look at the part C. So we talked about the second derivative of a function. How do we find the second derivative? That means just take the expression, so part C. So we had found the derivative was 2x, and then we can apply the same formula to find the second derivative of f, which is going to be easy if this 2x is not a complicated function. So to find the derivative of this function, we will apply the same formula. Let's call this g of x so that we have a better notation when we write the formula. So consider, instead of the f of x, f prime x, just call it g of x, and you will find its derivative. Okay, so whenever you put a prime, that means you are taking the derivative. So what we are finding here, let me show here. We are finding here the second derivative of f. Okay, so just for simplicity, I think I switched to the g notation so that we don't keep putting primes and primes. Now, how do we find this derivative? The limit as h goes to 0, like we had here. So just write it for g. The g function evaluated at x plus h minus evaluated at x over h. Okay, so this is the derivative function. And what is g of x plus h? Since g multiplies everything by 2, it is simply going to be 2 times x plus h. minus g of x itself, which is 2x divided by h, as h goes to 0. Any questions so far? So now we are just finding the derivative again of the function we had found for the derivative of f. Okay, so 2x is the derivative of f, and we are going to finding the derivative again. That's going to be the second derivative of f. Okay, what does this simplify to? The limit. So what do we have in the numerator? 2x plus 2h minus 2x. So 2x's will cancel out. So we will find 2h divided by h. And we can also simplify. So after we subtracted the 2x minus 2x, we have 2h over h. So these will also cancel out. So what do we find for this limit? Simply 2. Okay, and we will discuss this in a minute, after we are done with these. So what did we find? We found the second derivative of f to be a constant value 2. Okay, so let me highlight these and let's graph both. And we would like to also graph the constant function 2, y equals 2. Okay, so this is what we found. We found that the second derivative is 2. Okay, so let's just graph it. The only thing is I will just get rid of the original graph so that we don't have lots of things around. Oops, not this one. Okay, so now the black line is the graph of y equals 2x, and the purple line is its derivative. Okay, so what do we see here? So the derivative is always equal to 2. Okay, so the graph here, when you check, the value of the derivative is always 2. What does that mean? It means that this black graph, which is this black line, which is the graph of this function 2x, it has a constant slope. Okay, so this is the line that you are already familiar with. So this is the line y equals 2x, and the slope is 2. So you can also read from the equation. It is in slope-intercept form. So this is the linear function. The graph is a line which has a constant slope of 2. That's why the derivative is a constant line. Okay, so it is not changing like we had in the parabola. The derivative is constant at 2 because this graph of the function has a constant rate of change. Let's talk briefly about continuity and differentiation, derivatives. The relation between derivatives and continuity. If a function is differentiable at a point, then that function has to be continuous at that point. And if you read this statement in the other direction, which is also correct, what we should know that is that if a function is not continuous at a, then that function is not differentiable at a. So we can see how this applies to different functions. So let's look at these graphs. Let's start with the first one. Is this a continuous graph? Is this a continuous function? Because there is a hole or what we call a removable discontinuity. But this is not discontinuous. How about the second one? Is this a continuous function? No, there is a jump discontinuity. How about the third one? Is this continuous? No. Well, in fact, let's call these points A, where we have discontinuity. So all these functions are discontinuous at A. So we cannot talk about derivative at A. Okay, so these functions are not differentiable at A. Okay, at x equals A. So the first, in fact, this is like the second statement. Okay, if it is not continuous, it is not differentiable. Okay, let's look at the fourth graph. This is continuous, right? I didn't ask you, but I believe you would say so. And this is differentiable at all these points. Okay, we can find the derivative. So differentiable means it has a derivative, right? Differentiable at A means that the derivative exists. Okay, differentiable means the derivative exists, and that's how we usually use it. And taking the derivative we call like differentiate. So differentiating a function means taking the derivative. So differentiation is finding the derivative. Okay. Okay. So this case is a continuous function and it is differentiable. Okay, it's an example of a continuous function which is differentiable. Look at the next case. So let me get the purple. So look at this case. So here at A, although the function is continuous, the derivative does not exist. Okay, so the derivative, and we will discuss why. So derivative at A doesn't exist. Okay, why is this the case? So in fact, whenever you have a sharp corner, okay, so whenever you have a sharp corner, this is like the graph of the absolute value function, then we won't be able to have a derivative. And why? Because if you approach to that point from the right or from the left, you will have two different tangent lines, right? So the secant lines on one side will approach to a positive, to a line which has a positive slope. And if you approach A from the other direction, you will have the tangent line with a negative slope. Okay, so the two different tangent lines. That's why there is no derivative at that point. And similarly, in this case, so here at 0, consider the point 0, so the tangent lines become vertical. So whenever you have a sharp corner, or in the last case, we have a vertical tangent line. Okay, at 0, the vertical tangent line, normally we say that the slope is infinity when you have a vertical tangent line, but we say, in fact, this is how we call it, we say that the derivative does not exist. Okay, so whenever we have sharp corners or vertical tangent lines, we say that the derivative doesn't exist. If the function is differentiable, then we say that it is continuous. However, when the function is continuous, it may or may not be differentiable, like these two cases. Okay, so most of the time we will have continuous functions where we can find the derivative, but the other cases are also possible. Now let's talk about rules which will make our lives easier when we are finding the derivatives. So this is about section 3.3, differentiation rules. So let's look at the easy, like the basic rule about constant functions. Okay, so we will derive this together, we will find this together. Let me first write the result and then we can talk about it. So if we have a function f of x equals c, okay, like f of x equals 2, f of x equals 5, any constant value. What do you think its derivative is gonna be? Now let me show you the graph and you might be able to understand, like find this from the graph. So this is an example of a constant function, right? So y equals 2. What is the slope of this function? What is the instantaneous rate of change at a point? A horizontal line, right? The constant function. The graph of a constant function would be a horizontal line. What is the slope of a horizontal line? Because it is not going up, it's not going down, there is no change in the y values. So the rate of change is 0. And we can say that the slope is 0. Okay? So whenever you have a constant function, you can say the derivative is 0. How can we show it? Let's do this as a practice. So the derivative of f, where f is the constant function, is given by the limit as h goes to 0. So you should just remember this how to write this formula, how to write this limit. I think I will allow you to have a cheat sheet for the exam, but I think it's a good idea to remember this expression, how we find the limit of a derivative of a function. So what is f of x plus h? Can you evaluate this function at x plus h, the f function? So this is our f function. So what do you get when you plug into this function x plus h? It is c. It's c. Realize that the function c doesn't depend on x. So whatever you plug in, you will find c. Okay, f of x plus c. So what do you get when you plug in x to this function? It doesn't depend on x. Whatever you plug in, you will find c. So the numerator is simply c minus c. As h goes to 0, so c's will cancel out. We will find 0 over h, which is 0. So what is 0 over h? 0 over any number is 0. So we can simplify this to say 0. So we can say the limit of 0 as h goes to 0 is 0. I'm just trying to clarify that we are not dividing by 0. Okay, we cancel this expression, like 0 over h is 0. We first say that, and then we plug in this limit. We just evaluate this limit afterwards. So we find it 0. Okay, so we showed it, we proved it here that the derivative of a constant function is 0. You also saw it looking at the graph, since the rate of change is 0. Now you can say that the derivative of a constant function is 0. So let's see what the power rule is. So if f of x is x to the power n, okay, so for this is called a power function, n could be any integer. So except, in fact, -1. For now, let's keep it positive integers, okay? So let's say n is any positive integer, and then we can generalize it. So n is a positive integer. This means the integer set z, okay? Then we can find the derivative of f. We put the exponent as a coefficient, and we decrease the exponent by 1. Okay, so this is a very, this is a rule that could easily be remembered. So this was our first rule, and this is our second rule. The derivative of a power function, a function of this type, x to the n. To find that, we just take the exponent to the front and decrease the exponent by 1. Okay, so I will skip the formal proof for any integer n, but we can just take like n equal to 3, and we can just work that out. If you check out the text, you will find how this is proven for f of x equals x to the n for any positive integer. And there is also in the textbook, it shows for x to the third power. So let us talk about how we can prove this, how we can show this for x squared function. Okay. So the derivative of f, remember the formula again, the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, so what is f of x plus h? Let's plug it in. What is f of x plus h? It is x plus h squared, right? And what is f of x? It is simply x squared divided by h. So this is how we will find the derivative of x squared. And we did a similar problem, in fact, in the beginning of this lecture. So how do we square x plus h again? It's going to be x squared plus 2 times x times h plus h squared. And we have x squared in the numerator divided by h. Okay, so what cancels out? X squared and x squared cancel out. So we did very similar calculations earlier today again. Now we can factor out to h. So we will have 2x plus h over h, which cancel out. So we find the limit of 2x plus h. And what is this limit? So we can plug in 0 for h, right, to evaluate this expression, which is going to be 2x. Okay, so what did we find? Now, this was our function. Okay, so we found its derivative to be 2x. And realize that although there is no exponent on top of x, x means x to the 1, right? So in fact, this rule, we could have applied it. So when you talk about x squared, when you find its derivative, the rule tells us to put the exponent to the front and decrease it by 1, which is going to give us 2x. So we could, we just confirmed that this rule holds for the x squared function for n equals 2. Okay, so the function x to the 10. Let's find its derivative. So this is the exponent, which will go to the front, okay, so you just take the exponent to the front, 10 times x to the 10 minus 1, which is 9. So the derivative is 10x to the 9. Okay, so simple enough, right? Let's find f derivative, f prime of x, if f of x equals 7, sorry, x to the 7. So the derivative of f will be, now the exponent is 7, so we will take it to the front and we will subtract 1. So it's going to be 7x to the 6. Now let's talk about more rules. Okay, and we will also, let's also remember the other, like practice using other notations for the derivative. So remember, when we say the derivative of f, we could also use the notation dy over dx. Okay, so which means the change, little change in y divided by little change in x. Or we could say d over dx of f of x. Okay, so you can say df of x over dx. This means how much the function is changing relative to the change in x. But this is how we usually write it. So we just put d over dx in front, and inside the parentheses we put whatever function we have. But these all mean the same thing. Okay, so you might see it in different notations, so I'm just going to be putting these rules in both notations. So let's start with the sum rule. If we have a sum of two functions, so, and you want to take the derivative of these two functions, their sum, this is equal to finding the derivative of f and finding the derivative of the g function and adding them. Okay, I will in fact just include x's in the notation. Sorry, let me just do it this way. So if you have a function f plus g, its derivative means the function f prime plus g prime of x. Okay, so this is the sum rule, and let's see how do we apply this rule. So let's find the derivative of the function x cubed plus 5. So what will be the derivative of f prime? That's going to be the derivative of the x cubed function plus the derivative of the constant function 5. Okay, so in fact I promised to use also the other notation, and in fact it's going to look better if we use the other notation, so let me put it here as well. So the d notation. So we can say d over dx of f of x plus g of x. Okay, the derivative of this function equals derivative of the f function plus derivative of the g function. Okay, so these are the two same statements written in different notations. So here I just use the first notation. The derivative of this function is take the derivative of x cubed, take the derivative of 5, and add them. Okay, let me show it in steps. So this is the function, and taking its derivative means just take the derivatives separately and add them. Okay, so that's what the rule tells us. Just you can separate the function into two and just find the derivatives and add them. Okay, so what is the derivative of x cubed? What is the derivative of the x cubed function? 3x squared, thank you. So the derivative of x cubed is 3x squared. We take 3 to the front and subtract 1 from the exponent. Plus, what is the derivative of the constant function 5? 0. So the derivative of x cubed plus 5 is simply their sum, which is 3x squared. So the derivative of difference of two functions, so if you want to find the derivative of f minus g, you can find the derivative of f, and you can find the derivative of g, and you can subtract the derivatives. Okay, so the derivative of the difference equals difference of the derivatives. So like a very simple and like a very intuitive rule like we had before, let's find the derivative d over dx of x to the fourth minus 3, or let me just minus 7. Okay, so this is how we can ask for the derivative. So we want to find the derivative of this function. So the difference rule tells us that we can just find the derivatives separately. Okay, so we can find the derivative of x to the fourth and derivative of the constant function 7 separately and subtract them. So what is the derivative of x to the fourth? Take the exponent to the front and decrease the exponent by 1. So we just use the power rule. How about the derivative of 7? So this is a constant number. That's right, it is 0. So the derivative of 4x cubed minus 7 is 4x cubed. Okay, so in fact, we can talk about all the polynomials, but in fact, we should first talk about constant multiple rule first, which is very intuitive and simple. We have a constant multiple in front of a function. So let's say the function is x squared, and we have 5x squared. Okay, 7x squared. So we have some number multiplied by a function. And we want to find its derivative. Okay, so number multiplied by a function, its derivative will be c times the derivative of f. Let me also write it in the other notation. So d over dx, the derivative of c times f function, equals c times the derivative of the f function. Okay, so what do we mean? When you are taking the derivative of a function, any constant multiple, you can take it out, okay, and write it in front. Okay, so let's see an example. Let's find the derivative of 7x cubed. Okay, so the function is 7x cubed, and we will find its derivative. And we see that there is some constant in front, and the constant multiple rule tells us we can take it outside the function. So we can just take it out and find the derivative of the x cubed function. And we will just multiply the result with 7. So what is the derivative of the x cubed function? Just take the exponent to the front and decrease the exponent by 1. So the derivative using the power rule will be 3x squared, and then multiply the result by 7, we will find 21x squared. So let's see another example. Let's find the derivative of a polynomial. So let's do it in steps. First, realize that we have two terms, so we can just apply the difference rule. So we will find the derivative of each of them separately. Agreed? Okay, so we will just find the derivative of each and subtract. So this is the difference rule. And there is some constant in front, so we can take it out as 2, and we can just find the derivative of x to the 5th. And similarly, we can take this 3 out and find the derivative of the function x. Well, once you learn these rules, you won't go through many steps. Like in one step, you will be able to find the result. So I'm just writing openly for now. So we took out the 2 and 3, these coefficients, outside the derivative using the constant multiple rule. Now, what is the derivative of x to the 5th? So we can apply the power rule to find its derivative as 5 times x to the 4th. Minus, we will take this 3 and multiply with the derivative of x. What is the derivative of x? So this is the graph of y equals x. What is its derivative? Well, you can just consider it this way. This is the function x to the 1, x to the first power, right? And just apply the power rule, take the exponent to the front, 1, and decrease the exponent by 1. So you can apply the power rule to find the derivative of x. And what do you get? You get 1 times x to the 0, which is 1. And realize that this is just the function y equals x has a constant slope of 1. This is consistent, right? You can consider it geometrically or using the power rule that the derivative of x is 1. Now, last step. So we just simplify this expression. 2 times 5 is 10, x to the 4th minus 3 is the derivative of this function. Now it is time to talk about the product of two functions. Product or quotient of two functions. Okay, so we have a product of two functions and we would like to take the derivative of this expression. So finding the derivative of a product means, it simplifies to finding the derivative of the first function and multiplying it with the second function plus doing the opposite. So doing it in the other direction, finding the derivative of the second function and multiplying by the first function. So I will just write it in other notation. So if you have a product of two functions, finding their derivative means derivative of f times g plus derivative of g times f. Okay, so the derivative of the first function times the second function plus derivative of the second function plus the first function. Let's write an example. Okay, so this was, we will make use of this rule. Okay, how do we do that? So in fact, we can call this as the f function, and this is the g function, like the two functions in the formula. So when we find the derivative of the h function, which is product of f and g, so we should find the derivative of f. We will multiply it by the derivative of, we will multiply it by the g function, plus we will find the derivative of g and multiply by the f function. Okay, so just they take turns in having their derivatives. Okay, so what should we put for f prime of x? So the first function is x squared plus 2. What is the derivative of x squared plus 2 function? What is the derivative of this expression? So we can just take the derivative of x squared and take the derivative of 2 and add them, right? So what is the derivative of x squared? Take it to the front, take the exponent to the front and decrease the exponent by 1. Plus, this is a constant function, its derivative is 0. It's going to be 2x, right? So here we will have only 2x. The derivative of x squared will be, the derivative of x squared plus 2 will be 2x. For the second parenthesis, we will simply type the g function, which is 3x cubed minus 5x. Okay, so this is just the function itself, the second function. And then we will add to these the derivative of the second function. So let's find that the second function, g function, is 3x cubed minus 5x. What is its derivative? So it has an exponent 3, and it has a coefficient in front, which is a multiple, constant multiple. So this 3 will normally, we will just apply the power rule for x cubed function. It's going to come down. When you also apply the constant multiple rule, in fact, they will be multiplied. So in fact, you can combine the two rules. So the derivative of 3 cubed will become 3 times 3, which is 9x squared. Okay, that's right. So we applied the constant multiple rule for this 3, and we applied the power rule for this 3. Okay, so when we take it down, it's going to be multiplied by this 3. We will get 9x squared. Minus, what is the derivative of 5x? So now we will subtract the derivative of 5x, which is going to be 5. Okay, again, because the derivative of x is 1, right? The exponent becomes the coefficient and it decreases by 1. So the derivative of 5x will be 5. So the derivative of the g function, so this was the g function, and we found its derivative to be 9x squared minus 5. And we multiply this with the f function itself, which is x squared plus 2. Let's look at the first expression. We will multiply, let's simplify, multiply 2x by these two expressions, which is 6x cubed minus 10x squared, right? Plus, we should just FOIL out the first terms. 9x squared plus x squared will be 9x to the fourth. And 9x squared plus 2 will be plus 18x squared. minus 5x squared minus 10, right? Minus 10. So we can just simplify. So we have 6x to the fourth plus 9x to the fourth, which is 15x to the fourth. So we have a couple of x squared terms. Negative 10, negative 5 is negative 15x squared plus 18x squared will be plus 3x squared minus 10. Okay, so we found the derivative of the h function by applying the product rule, the quotient rule. And this is the last thing we will discuss, which is very similar to the difference, to the product rule. So we talked about the product rule. Now let's talk about the quotient rule. So this is about finding the derivative of a quotient of two functions equals the derivative of the first function. By first, I mean the top function, okay? So the derivative of the first times the second function. So this, until this part, we start with like we did with the product rule, minus, so instead of plus in the product rule, we have a minus in the formula. The derivative of the second function times the first function. Okay, so realize that the top part, this only differs from the product rule by a minus. In the product rule, we had a minus, a plus, now we have a minus. And we also have a denominator, which is square of the g function. Okay, so square of the function in the denominator. So let me write an example. Let's find the derivative of the k function. Okay, if the function is 5x squared over 4x plus 3. So we can call the top function as f of x, the top function, and the bottom function, let's call this the g function. And then we will find the quotient of these two functions. So the derivative of k, how do we find it? Just plug it in this formula. So in the formula, we will have the derivative. So we start with the derivative of the first function, right? Derivative of the f function, which is 5x squared. What is the derivative of f? Let's find it here. So what is the derivative of this function? Apply the power rule and the multiple constant multiple rule together. So take this 5 to the front, which is going to be 5 times 5, 25, x to the fourth. Okay? So in the formula, wherever we have the derivative of f, we will put 25 x to the fourth times the g function, which is the function in the denominator. Okay, so the function in the denominator, that is 4x plus 3. Minus, which comes from the formula, we will put down the derivative of the g function. So what is the derivative of the g function? So this is the g function, and its derivative will be simply 4, because the derivative of 4x is 4, derivative of 3 is 0. So here we just have a 4, okay, 4 for the derivative of the g function, times, look at the formula. So we had here the derivative of g, and in the formula, okay, we have the f function, 5x squared. So 5x squared, when you take the derivative, you will find 5 times 2, which is 10, x to the 1, 10x. Okay, so we put it here, 10x. So the first top function's derivative times the bottom function, just copy it here, minus, which comes from the formula here, okay, minus the derivative of the denominator. So the denominator, the bottom function is 4x plus 3. Its derivative is 4 times the top function. Okay, the function itself. We just multiply by the top function. So they take turns in having their derivatives. Then we will simplify this expression. It would be, okay, let me see. And in the denominator, what do we have? We have 4x plus 3 squared. Okay, so I just take the square of the denominator. So what do we have? Let's multiply. So let's multiply and find the numerator. 10x times 4x. So we are multiplying these. Will be 40x, right? Sorry, 40x squared plus 30x, right? 3 times 10x will be 30x minus 20x squared.